specific to a material orientation then, I guess. Like, how do you assign the reference axis when you're meshing, or there's no way to assign it. You have to actually rotate the mesh.
Um,
Like, can you
I
show
think
that
it's
process, I guess, or
yeah.
show me
So
what you do?
yeah, I can do. I can look at one of these the tensile simulations, and we can work through one of those. So for this one here, I can look at the material axis. If we do that,
Yeah. Okay.
this is what we see, and this corresponds to the input, right? And now if I want to,
So instead of rotating the mesh elements there, can you just change those indices in the material axes there? Like if you change the 001 and you start changing those around, does it have the same effect as rotating the material?
I don't. So that's not the approach I took, because doing this, I think I have to specify the element. I'm not too sure if that's possible
Okay.
to do manually.
I
But
mean,
the
what
way
you're
I do
doing
it,
is like a surefire, clear way of it, but I'm just saying from like automation perspective, if you were to do this with your neural network stuff,
yeah.
it would be easier, I would think, to automate rather than rotating. The rotating process is harder to do than changing those indices, I think.
Um, Not necessarily, because it matters how the geometry is imported, which orientation.
Oh,
For
okay.
example, now if I wanted to have the material axis changed, what I would do is I would just rotate this object, the z-axis,
Yeah, okay.
and now if I mesh it, the material axis 1 should be facing the other direction, the y-axis direction. Or material axis. No, sorry, material axis would still be facing the x. I have to look at that. Yeah, my bad. So material axis 1 still remains the same. It's just now the orientation of the
Okay, understood.
geometry has changed.
Okay, I probably derailed what you wanted to ask me because I was asking intermediate questions there. What was the question, I guess the reason for setting up this meeting? What was the stuff you wanted to clarify?
So the stuff I wanted to clarify was the actual model setup itself. So I followed what the boundary conditions assigned that Beza said to use, and I followed those. And then, see, what I'm confused is looking at the strain tensor. I can pull that I can get that information. So if I were to look at the simulation, so that's why I attached the simulations for you to look at too. So like maybe after this meeting, or maybe we don't need to do that, but like what you can do is you can click on this icon here.
Okay, let me see if I have that because I have the simulation up.
Okay.
So what's then, I mean, that has something to do with node definite, or I guess node selection, that icon,
Yeah,
or
this
what's
is
the,
node selection. But with node selection, you don't really, you're not capturing the integration points, you're just capturing the displacement
the
of the
mesh
nodes.
nodes? Yeah, okay.
So you can see that information. You can see the direction it's pulling and all that stuff. But to analyze the actual stress strain, you have to click on the element data icon and go down to deformation.
Yeah.
And you can look at, and then the effective strain is pretty much calculated at the center. So to get the stress components, you have to look at the integration point itself, and this is what I get. So I get the 6 values of the matrix, but
These are just
I'm
nodal coordinates, right? Or is this
these aren't the
strain? Oh no,
nodal
it's just
coordinates. These are
stress.
the actual stresses
Okay, yeah.
at the integration points. I believe it's points. I think this is like an 8 brick element. And then you also have the strain component. You have, like, none of these are active, so total component. Here, the thing is, for pure shear, these should be 0, right?
Yeah,
And just,
the deformed shape that you have on the screen here doesn't look
yeah,
like pure shear though. That's the problem.
exactly. So I like, that's the boundary condition here. That's my confliction there. Like, I'm conflicted there because I'm following this exact approach. I also ran a
Okay,
couple of other
okay.
simulations with what pure shear is supposed to look like,
Yeah.
and those are also I, they're not giving me the right answer. So I guess we can take a look at those. But
Okay,
before I,
before you jump forward, the X, Y, and Z strains here, you have negative 13%, negative 5%, and positive 19. Go back to the stress components for the axial stresses. Negative 50, negative 40, and then 0.64 megapascal. Yeah, the strain, like when you 5% positive should be more than 0.64 megapascals,
hmm,
which is weird. But anyways, the other, at least it's negative, negative, positive. Um, Go to your boundary conditions. I think that's probably the next step you were gonna
yeah,
highlight.
yeah. So for the boundary conditions, I'll have to go to this thing here. Hold on.
So it looks like it's imposing a Z or a vertical boundary condition, sorry, a Y boundary condition on one of the nodes, and the other node is not. It's pulling diagonally on one node, and the other one is just moving laterally. So, okay.
Um, so the fixed one, this node, right,
Sorry,
that
point to the thing again.
uh, it's very small.
Oh yeah, okay, the
Right
red
here.
dot. Yeah, yeah.
Yeah. So that is fixed. The Y, this bottom face, the nodes in the bottom face is fixed in the Y.
Okay.
In the X, the 2 corners here are fixed.
Okay.
So now I've pretty much covered the boundary conditions in the diagram. And for a positive Y, I'm applying a nodal displacement of, or velocity of 0.1 millimeters per second up for all of these guys, for these 2 corners.
I think that's the problem. I think you need to move laterally for that one. Like keep it in a constant orientation. Can you make them
Isometric.
or yeah, either isometric and then make the shading transparent.
Okay. Yeah. Actually, I'll go to the other view I had.
Yeah.
Uh,
Whatever orientation you were thinking in, just put it in that orientation.
yeah, this is the orientation.
Okay. So show me the ones that are fixed, like start all over again. Yeah. Okay, so that is fixed in the Z is fixed. Go to the first one. Let's just double check. That's fixed to move in and out of the page.
Yeah.
Okay.
Y is fixed.
Yeah.
X is fixed.
So those points are fixed in space in total.
Yeah.
They can rotate, but they can't translate. Okay.
Yeah.
Now go to the other that one.
So this one pulls up in the Y direction,
Yeah.
these 2 points. And these 4 points pull in the X direction, positive X direction.
Yeah, so I think the problem is you're applying those simultaneously. This is one boundary condition where you're pulling in the X, but you're not pulling in the Y. Simple shear is, I'll give you a diagram here. Maybe I can post it to the chat. Simple shear is these fixed in the Y direction. Those 4 points are fixed in the Y direction, and you're
Yeah.
only pulling in the X. That's what you have, I think.
Sorry. So, oh yeah, that's simple shear. We're looking at pure shear, right?
Pure shear.
So I
Oh,
did
okay.
do simple shear. Um, Simple shear was this guy here, I think.
Okay, in that case, what you're doing is pure shear. Yeah, that's fine.
Oh, I got two.
Part of the issue with pure shear is that the bottom two nodes. I don't know. You probably can't see my screen here. Just allow me control, I guess.
Yeah.
Okay.
Oh no, it's not it. How do I think they changed the teams. High jump.
Yeah, you have to share your screen again, I think. Okay.
Oh yeah. Okay. Here we go.
Okay, so these two nodes here,
Yeah.
those should be allowed to move vertically.
Mm-hmm.
And you're not imposing boundary conditions, but for some reason, when you go back to the deformed shape, uh, wherever that is, they're not moving vertically. These are
Yeah.
fixed in the Y direction. So why is
Okay.
that happening?
So I ran that simulation. So the what you're referring to, I ran that with the Y boundary conditions turned off.
Okay.
I think this should be the one.
Yep, that looks correct.
It looks correct, but again, I'm not sure about total. So for this one, now we're looking at the stress.
So this makes way more sense because you have X and Y stresses induced and basically nothing in the Z. And they're equal in the X and Y direction.
Mm-hmm.
So if you think about pulling like that, like
Yeah.
you're pulling this one corner, what
Yeah.
is going to happen to the side lengths here and here? Are they getting longer or shorter? I mean, when you parallelogram it like that, these will get slightly longer, meaning
Mm-hmm.
that you have a tensile induced stress. And there's nothing in the through thickness direction, or virtually nothing.
Yeah.
So that kind of makes sense so far. And the strains there are 0.7%. I think that's what that is.
Mm-hmm.
Yeah, the Z strain seems a little low, but sorry, high, because you have less strain in the X and Y direction and you have more stress. But it could be because of the Hills coefficients and shear and compression is slightly different. But okay, anyways, go ahead to what your question is. If these numbers make sense, is that your question?
Yeah. So that analysis makes sense, and so I don't know where the connection is between what I'm saying and what I'm going to show you. When I look at the stresses here, like these stresses, so what exactly am I looking to confirm? Because I'm trying to confirm the LMN coefficients, right? Whether they're correct. And I know the shear stress values that I need to get. So stress in the XY is 17 MPa, and XZ and then YZ is 21 MPa for the XY, the model in the XY plane.
That's
It's
what
just a
Bezod mentioned, or
connection.
that's what the model's telling you?
This right here.
Yeah, where did you get 17? I don't see the number 17 anywhere.
Here. So these are from the, this is from Bezod's Hill's coefficient calculations.
Yeah, okay, I see this now. Okay, it's in his email. Yeah, compare the simulated. So those are experimental yield stresses,
Mhm.
X, Y, and YZ.
And I can understand that. So this is Bezod's coefficients. So they seem kind of off. So like the shape of the deformed shape seemed kind of off. So okay, that might be the case. Hugo's coefficients in that case, based on how well the deformed coin shape, how similar they were. I think Hugo's coefficients, Hugo's XY stress value should be closer to what we see here.
Okay.
I might have. Yeah, I don't think I ran. I can run that one right now, and we can verify that. It'll take a couple of seconds. I think
Sure.
I saved over it or something. So yeah, that was the thing. I just want to verify, like I'm looking at the right information to make this bridge to see if I'm doing it correctly.
So Bezod's diagram there that has the boundary conditions imposed,
Yeah.
it says his intention is to generate pure shear, and
Mm-hmm.
um, what we're doing here is slightly I mean, it is pure shear what you're getting, but
Yeah.
it's not the same. His boundary conditions are kind of incorrect. I would say node 3 and 4 should not have a Y constraint on it.
Mm-hmm. Mm-hmm.
But he's imposing a Y constraint and then he's adding a load in that direction, which doesn't make sense to me. But anyways, continue with what you were saying.
Um, one interesting to note here is that if I draw the, what was it? What did I do? Load. Summary. So the effective stress curve matches the curve. I just want to point that out here. I can really
So there's two curves line on line right here, or no?
what's that?
Okay, this curve matches the material curve that you're inputting.
It's close. I think here. Let me. This is from. This is not from our pure shear one, by the way. This is
Okay.
from, right? Let's close this one. Strain. Wait, no, it should be this curve, the 0.1 here. That's this curve here.
Okay. So this one flattens out and the one that we're looking at here tapers up.
Sorry,
So the strain rate that you did here, what was the imposed velocity?
0.1.
Okay, so your max is about 70. Yeah, that looks good. Other than what's happening
That
here, but
what's happening there, and that's probably just because when we get to this point, our element starts to distort.
deform. Yeah. Okay. Um,
This kind of flow curve, obviously, we don't see in our pure shear case, which I guess makes sense. But if you ask me to explain that, I wouldn't be able to explain it. As
okay,
to
so I
why.
think I still don't think the boundary conditions are lining up with what Bezod is looking like. That's not the correct deformed shape at all.
For pure shear, yes, yeah.
Uh,
So I'm going to go back to setting up Hugo's material model with this model and see if we get
okay.
a closer X Y value.
Because ideally what you should be getting is no axial stresses. If it's done correctly and the boundary conditions are correct, you should just
Yeah.
be getting shear stresses, kind of
Okay.
intuitive with the name pure shear.
Okay.
So if you're getting any axial stresses, most likely you're over constraining the nodes.
Mm-hmm. Mm-hmm. Oh, what was this one?
I'm kind of taking notes here on your process flow. So in the event that you're going to need to, or we'll carry on some of these simulations, which I think is less important now because your comp got deferred a little bit.
Yeah. Yeah.
Um, at least I have somewhere to go from and not bug you constantly with.
Yeah. No, and it's fine. Like if whatever questions you have, it doesn't take me long to, because using the software itself, I've been using it for so long that I'm kind of familiar with the ins and outs of this, so
Yep.
it's not an issue.
Yeah, I think the boundary conditions that Bezod asked you to do are not correct.
Okay.
That looks okay. Now go to the in this direction, it's correct, but go to the ISO view.
Oh, you want to
Yeah,
see the other
yeah.
side?
Just yeah, look at a top view maybe. Yeah, that is incorrect now. That's the reason
Mhm.
why you have those
It's
stresses.
collapsing. Yeah, or inwards.
So this side length for some reason is expanding, or this one is this one's held rigid, and these ones are
Yeah,
allowed to expand. Actually, that's the problem, is these are the two nodes that you've constrained, no?
constrained. Yeah, yeah.
So
Sorry.
why is it over constrained?
If I were to, so this is the other thing that I noticed. If I were to set constraints to these faces, Z constraints, well, I guess I would only constrain one face.
So you need one node totally constrained for translation, and then the other
Yeah.
one, um,
Okay, I might have missed that. So what
yeah,
you're saying is I need to constrain
Only
This
one
this
corner.
node here in the z-axis.
Only one of them, yes.
Well, okay, let's go
Actually,
back.
this really is a two-dimensional simulation that you're trying to run. Okay, so
Yeah, yeah.
you don't want to have the thickness direction, but you need to because it's obviously a three-dimensional element that you're using.
Uh-huh.
So yeah, I think
I
either
have,
constrain this direction on both sides or unconstrain it and see what the results are. I honestly, off the top of my head, I don't know. But your deformed shape in the 2D plane looks right, but you're having 3D stresses induced because you have this hourglassing shape.
yeah, yeah. Um, yeah, okay. I'm gonna constrain that right now. We can run this again. One thing that I did notice was when I constrained both faces, the simulation doesn't
Run,
um,
convert.
run. It doesn't run. Yeah. Um,
Uh,
XY. Let's get into the orientation. I'm going to fix this node in the Z direction. So
realistically, you could fix try fixing 1, 2, 3, and 4.
three,
None of
yeah,
them
yeah.
should
I'm
be
gonna fix
moving in
this
the Z
entire
direction.
face,
Yeah.
and leave this face untouched because when I do that, it crashes.
Yeah,
It does.
exactly. If there's no, okay, yeah, agreed. Yeah, so go back to your Z constraints here and the nodes that you're applying those to. You don't need two of these. You just need one whole face Z constrained, and then in the thickness direction, you're allowing everything
It's a
to expand.
span. Yeah, okay.
See, this is why I hate doing single element, like Bezod for some reason, even Jahed loves these single
Yeah.
element simulations, but it's so difficult to talk about it because it looks the same in all the orientations. Where when you
Hmm.
did the rod that you did that with 30,000 elements, it's a
Yeah.
way easier to point and look at stuff.
Hmm.
Anyways, continue.
That's what I'm finding. I didn't think this would take me this long, but okay. So right now we have this face constrained, Y down here constrained, X constrained here, and then Y pulling positive Y, positive X
Yep,
displacement.
that's fine. So go to the Z again. Which nodes are constrained in Z? One whole
One,
face.
two,
Yep,
three,
perfect.
four.
Okay, run that. Hopefully it doesn't crash.
I don't think this is going to crash because we have that other face unconstrained.
Yeah. The other thing that you can do to like simplify this type of work is deactivate the strain rate effects and only look at one material curve. Like right now it's you're imposing a velocity, but the
Yeah,
velocity is the velocity gradient throughout the element is changing.
it's
So
changing. Yeah,
that's why when you're looking at the material curve, it's
yeah,
slightly interpolating at the end between a
yeah.
slow and faster. It's not always zero point 0.1. It starts as zero point 0.1, but it's not always zero point 0.1. Hopefully
Mm.
that gives you the explanation that you need. But if you just
Okay, yeah, that makes sense.
if you remove strain rate effects, you know it's
Yeah.
always referencing that one material curve. And to be honest, for what you're trying to do, the strain rate effects are irrelevant. I
Mm-hmm.
think, at
I mean,
least.
that's a good point. Okay,
Yeah, okay,
everything
that
looks
looks
good.
better. Okay, see the stresses that you're getting? 19.
That's
Okay. So is
that's
it
X. 19 and XY.
And it
And
that was supposed to be, let's see here.
17.
Yeah, 17 and then 21 in YZ, which
Yeah.
that's not getting 0. Okay. Rotate the deform shape here. Okay.
You have control. Yeah.
Yeah, well, we both have control, which makes it very confusing, but what can be the reason for this?
So in a situation like this, if you press F3, it'll center crop. Yeah.
So you have positive.
The one downside with the element model is I can't visualize the material axis. Like if you
Yeah,
click on
yeah, yeah.
material axis, it doesn't show you the vectors pointing in the right coordinate system. So it gets kind of tricky to verify it's correctly oriented.
Okay, so are these the nodal stresses, or it says integration point stresses?
Yeah, so those are I don't I'm not 100% sure, but those aren't the nodal. I don't think those are the nodal stresses. I think that's the stress at the center of the element. Like it interpolates that the integration, the stresses at the integration points, and then gives you one single value at the center of the element. I'm not entirely sure if that's correct, but that's my intuition.
So this strain rate plot here, XY is the strain rate that you're imposing, and it's around 0.1, but it's changing throughout the simulation, and all of these other strain rates are non-zero. So
Uh-huh.
that's where that extra deviation in the flow stress behavior comes from at the end when it starts kicking up. Because as you go towards the end here, like
Yeah.
these numbers are now large, not large, but they're not e to the -7.
Okay.
So that's part of that problem. But
So that
uh,
should get resolved if I remove the other strain rate curves.
if you
And
disable the strain rate hardening or strain rate effects, yeah, and make it one strain rate curve, yeah,
yeah.
that should fix that problem. But it still has some XY component of stress, which is weird. Like these should, all three of these should be 0.
Be
You should have
zero and that, yeah.
20, sorry, 17 and then 21.
Mm-hmm.
Let's make sure that we're having the same rotation.
Oh, I think my computer froze. Oh no.
Yeah, okay.
Are you able to? Yeah. Okay.
Yeah, I'm just looking at my other screen.
Okay. Uh,
Is there a way to look at the equivalent stress?
equivalent stress should be right here. General. The effective. No. Yeah. Effective stress.
Okay, let's. So if we plug in the values into, or we calculate the von Mises equivalent stress, let's say from the values that we're expecting, That equivalent stress, let's see if it matches. Okay. Okay, so the equivalent stress was 40 something,
44, yeah.
44. Okay, so what from what Vezod was mentioning, or I guess asking to happen, I don't know if I can send this picture in the chat. I'll WhatsApp it to you actually.
Okay.
This is what Moore's circle will look like for what we're doing. So you effectively you have a big stress tensor, like a 3 by 3 stress tensor because it's 3D problem. On the diagonal of the stress tensor, you have 0, 0, 0 because those are your hydrostatic or axial stresses. And then we have 17 megapascal in XY for shear and 21 in YZ and 0 for XZ. So this is what the components should look like. This is what
Yep.
your Morse circle should look like. And then
Mm-hmm.
your von Mises equivalent, which I think is what that effective stress here is giving you, says
Yeah.
it's 46.7. What you're getting
Okay.
is 44. So somewhat close, but not totally correct because you have these XY stresses.
Mm-hmm.
Why are there XY stresses being generated? Okay, go back to your boundary constraints. Okay, sorry, just these two nodes. I think the ones that we're fixing are totally fine now, but the ones that you're applying velocity to, this might be the free distortion. So what you're doing here, I don't know if it's actually constraining the other directions when you apply a y velocity or if it's only applying the y, because probably instead of applying these independently, is there a way to give a vector? Or do you normally, if you want to have a diagonal velocity applied, you normally have the components of the vector defining the velocity?
That's the way I've been doing it. Free distortion, boundary conditions.
Not to fix an XYZ. I'm not sure how this works, but I think because you're defining these independently,
Yeah.
it's
Yeah.
it's adding some virtual constraint somehow.
Okay. That could be.
Like
Okay. So
what is all? No, not all. You can't do all. Uh, Go back to the deformation. Like, how did you add an additional constraint here? What buttons did you click to
so
get
to
to
add
this?
You have the velocity, and
Okay.
then if you, so you can, on the left here, you can select specific node.
Okay.
I don't know what this stuff is actually. Well, I think that's select anyway. And then you can specify the direction and velocity and click on the node. And then you click this to add.
Okay. What are the other options on the left toolbar here?
So this allows you to pick the entire face, like this here.
Yeah. Okay.
This allows you to pick a specific
Node.
node.
Can you pick edges?
Uh, no, I don't. As far as I know, can't pick edges because this is applying velocity
Okay.
to the node. Um, if you go to forces, yeah, it's same thing. You have to.
What does
Would
movement mean?
force work? What's that?
Yeah, I mean anything. It doesn't have to be a velocity. It could be a unit force. That's
Maybe
fine.
force. Do you want to try that?
Sure, yeah.
Using forces instead of
Yep.
velocity.
Yeah, that might be the problem
Mm-hmm.
because those velocities are getting applied simultaneously, but I don't know if it's applying an additional constraint to force those
Uh-huh.
nodes to only go in that direction.
Yeah. Okay.
But if you
Let's
apply
let's
the
try that.
force, if you apply the force, it's just going to resolve the deformation based on whatever the force resultant force vector is. Yeah, try
Yeah.
forces.
This is yeah, you're right. That might be useful. Let's try that.
I mean, this is relevant for forging because you're viewing the forging die as like this radically strong thing that's just
Mhm.
crashing into the deformable shape, the billet, and
Yeah.
it's rigid and you're imposing a velocity. But in reality, it's if you program the force curve into it, that would be more realistic. Instead of
Mhm.
doing displacement control
Yeah.
and monitoring the force, you're doing force control and monitoring the stroke. The yeah. Anyways, try forces and see what happens. It's kind of dumb how you can't program a vector though. Is there a way to create a local coordinate system?
um,
Don't
I
worry
don't
about that now.
think it's
Actually,
possible. Like in
just try the
Abacus,
forces.
um, I'm gonna put 10. I don't know if that's right. Whatever.
Okay. The
These are
vector
all.
sum of that is 14. Okay, that makes sense. Root 2 times 10.
Yeah. Yeah, that's good, right?
Yep.
Yeah.
Your deformation is going to be a lot smaller now, so you're going to have to scale it to view it like you were before.
Okay.
But we'll see if you have no axial stresses, then that's good.
Mhm.
So is this like a job manager here? It's a queue that you submit to the analysis solver. This window that you have brought up. Is this like a separate running window within
Yeah,
DEFORM?
so what we opened up before was the preprocessor. That's the environment we do all the
Yeah,
setup and
okay.
everything. And here we can queue up the simulations once we generate it. We can run it, queue it up, yeah, and then post-processor,
Yeah.
3 modules. This thing isn't working, so there's something wrong.
Fatal error.
Not too sure. I mean, the other thing is we can just run a shear hat test.
Yeah, I mean that's ideally what I'd like to eventually do, simulating a shear hat test and then correlating that to the shear hat data that we've got. I think
Yeah.
that that's a powerful thing because a single element looks stupid in publications, in my opinion. But this is I mean, we need to get confident with um, the boundary conditions and all of that first.
Yeah.
So,
Okay.
but go back to let's see what the error messages were, and
The error
then
message here. Here, read this. I'll be back in a minute. Just give me one second.
okay, no problem. Okay, so I think I have an idea. One
Okay.
thing that we took for granted is your single element. I didn't even look at what the scale of it is, like how many millimeters of side length is it? 10
What?
newtons of force might be way too much.
Yeah. Okay. Yeah, yeah,
So
yeah. That makes
maybe one
sense.
Newton of force.
Yeah.
I
Yeah.
don't
Yeah.
know because it's saying that the deformation is high. That's probably it's actually iterating and getting two or three iterations in, and it's dying because
Yeah.
10 newtons is probably way too much.
Yeah. I think you're right. I think that is the issue. That. Yeah. I've noticed this before.
But I mean, if it's a 1 meter side length material, then obviously that's not a problem, but it's probably not 1 meter in side length.
Mhm.
I don't even know what, the forces are in newtons. That's the unit system that it is. Okay.
This is a 1 millimeter. This is a 1 millimeter cube. So that is probably the case. I think. Just to be on the safe side, let's do this.
There it gives you a nice force vector. Okay.
Mhm.
Now those mesh lines, where did they come from?
Those aren't mesh lines. That's just the STL file.
Ah,
So
oh,
the
okay,
mesh
okay.
is just
Yeah,
a
yeah.
cube.
Yep. Okay. Good old STL.
If this doesn't work, there might be another. Oh, okay, we're good.
That's stupid. Honestly, in reality, it should survive 10 newtons of force. Because I know maybe 1 millimeter cube. I don't know. What was the hotkey for auto fitting the viewer?
F3.
Yeah, that's it. Okay.
Okay, maybe that force was not enough.
Okay, well, can you amplify the displacement here? Like, is there a way to scale the deformation?
Yeah, again, I don't, it's not as versatile as Abacus. You can't
Okay.
scale it. I don't think there's a way to scale it like that. At
Just
least I don't.
go to the stress components. I agree that you're still getting
The same thing.
the same thing. Yeah. Shit.
Mm. Well, I am constraining this point here.
Hmm.
But then I have to constrain it. If not, it'll pull it. It'll rotate the object.
Correct. Yeah. Hmm.
Like this point here.
Yeah. Okay, go back to the boundary conditions. And make it wireframe if you can. Yeah.
Constrained in the z-axis.
Okay. Those two are constrained in.
There won't be any color.
Hmm. 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 Yeah, I think this free distortion BCC is uh, is the only way that we're gonna get what we want.
Okay,
But pick a node to fix in the X, Y, Z
we
direction.
can try that.
Yeah, so these two nodes, try doing that.
Yeah. Mm. Mm. Doesn't show me anything. It's weird. Okay, that's node 5. This is node 1. Okay.
Move X
Pick a node along y direction to fix in z direction. Along y direction to fix in z direction.
Yeah,
Pick along z direction to fix in x direction. Okay, so I think you're right. This is what we need to do because now we are pick a node along x direction to fix in y direction. This one here.
that's the Z direction though.
Oh yes, along y direction to fix in x direction. So y direction to fix in x direction.
Yeah, this is just removing Z, the rotation about Z.
So this one, back to this
But
one then, yes?
the rotation about Z is the rotation that we want. That's the rotation that's allowing the shear deformation.
Mm-hmm.
could. Okay, try picking that node. I don't think that's correct, but
Okay, that one's picked.
okay.
Just remove Z rotation. Okay. Forest. I'll just increase the forest to 1 or something. Does it
Sure.
matter? I guess not, right? Oh, okay.
That works, I think. Yeah, I'm not hopeful this is gonna work, but yep. I don't see deformation though. Mm,
1 Newton.
what was the amount of force? Like,
It was 1 Newton. That's what I put in.
sorry. Yeah, the stresses that you're getting in uh, that, or I guess that Bezod mentioned in the email of 17 megapascal and 21.
Yeah.
Those stresses are only occurring at the yield, I think. Like that, those are the peak stresses that he's quoting.
Yeah.
That those are effectively the yield stress in both shear directions.
So we do need to see this thing displaced in order to see those values.
Yeah. Uh,
Okay.
So yeah, I think looking at you need to plot the curve of tau xy and tau yz.
Tau xy and tau yz. Uh,
Like in this simulation, you're not getting past the yield stress because the stresses are only like 2 megapascal. But
yeah.
the one where you impose the velocity to the nodes instead,
Mhm.
that one it was deforming a ton. Like,
Yeah.
can you bring that result back up?
We can bring that up and assign the free boundary conditions.
I don't think the free boundary conditions fixed it. To be honest, I don't agree with the rotation about Z needs to be free.
Okay.
Just the one that you did um, with fixing the one face in the Z direction.
Okay.
So
Well,
like
I'll
the
have to
one that
rerun it
you.
because I
Okay,
saved over it, so I'll have to
no,
rerun it.
no problem.
Let me just
That's
close
good.
this desk.
This is teaching me as you're doing this.
Well, a lot of learning happening on my end. Oh yeah, I gotta do that too.
Honestly, I saw a mere Y, his entire PhD was with single element type simulations like this, and I'm like, how? But they're so detail oriented, like because there's
Yeah,
no design aspect to what they're doing, right? They're only looking at correlating an input curve to an output curve, and it's like, I don't know, it's
it's pure math, pure theory,
yeah,
and I don't know if I could do something like that
yeah,
with a single element. It's so boring.
yeah, agreed.
What was it? So let's get rid of these. I fixed.
That Y is
Oh,
wrong.
that's wrong.
Uh, that's what I was disagreeing with. I think that free distortion BCC is just an automated like walkthrough of setting up boundary conditions. It's not allowing you to do anything special. It's just if
Mm.
you don't know how to set them up, it's just asking you to do. It's like a step-by-step process to make sure that you don't have a model that will translate in space. Okay, go to the
Mm-hmm.
Y now. X is fixed. Yep, and the
It's
Y is
fixed.
fixed.
Why this guy had to fix it here?
Yep.
Why is fixed? Z is fixed.
Yep. That looks good to me. Is the you just have to add the velocities.
Yep. I'll get rid of the material curve too because might as well do that now.
Agreed. Is there like an initial starting menu where it asks you like, do you want thermal effects enabled? Do you want strain rate effects enabled? Like
So
this is
yeah,
isothermal right now. Okay, yeah.
you have to go to simulation controls and then um, you can adjust the solver and all that stuff. Constant. Yeah. Like here, if I want
Okay.
thermal effects, I need to
Yep.
turn it on. I don't think there are any other settings here that I need to
So there's
adjust.
nothing for strain rate. You just have to blow the other material curves out of the material model.
Yes, and for strain rate, there are some other options that you could mess with, and I'm not entirely sure um, what these are. So you have to go here. So there's I guess the cutoff strain rate, it may, like once you set this, I think when you get to a certain point, the element is assumed rigid. So there's something like that.
Oh,
I'm not entirely
okay.
sure.
Yep.
There's a couple of things there
What's in
with that.
deformation? The property. Okay, go to,
Deformation.
sorry,
Oh,
here, property and then deformation. Yeah, that one.
yeah. Oh, yeah. So this also, again, here you can control this. I think when you can access this at the help menu. There's this limiting strain. I think when it falls below this value, it starts to behave rigidly. I think that's the case. I have to verify that. I'm not entirely
Okay.
100% on that. Yeah, and
And
then you can turn on and off.
what's the Z rate here?
It's a good question. I'm not sure.
Okay.
We can
No,
look it up.
don't worry. I don't think it's affecting what we're doing. Don't worry. Okay,
Oh,
continue with what you were doing.
so I'll just clear out the material curves.
Yeah, go back. That's where how you adjust this. So here, see how you have E dot? Is there
Mm,
another model in the flow stress curve here that just has sigma, no E dot? Yeah, right here. Sigma is a function of A and temperature. So that, if you do that, this should only allow you to program one, or sorry, multiple yeah, never mind. You can do what you had before. But this material model doesn't have strain rate effects in it. But don't do this. Do what you had before. Sorry. I don't know if
The
that
A,
if
I'm
that
not sure what the A is.
yeah. Yeah, it's probably just easier to delete. Yeah, okay. Never mind.
Okay, this looks good. Yeah. Yeah, okay. Everything else looks good. I guess let's run this, right?
Yep, I agree.
Yeah, it's all the same stuff.
And the Hills coefficients are still in there. You never touch those, correct?
No, those are all Hugo. So we're running Hugo's model. So these are all Hugo's values.
Okay. That could be the issue. I mean, his coefficients, I don't think it's the issue, but
Yeah.
because they're only slightly different from Bezod's. It's not like one of them is zero or the other one is positive.
Yeah.
Oh, look at that. Fancy. Okay, so now what I want you to do is graph tau xy if you can versus versus increment or strain.
Tau xy. That is in the summary. I think I can do that actually. XY. The thing with it doesn't show up as,
Yeah, right there, that one.
yeah, this one is 0. So I think what I'll have to do is I'll have to export. Yeah, I think I might have to export this
Okay,
to get that
just do the
information.
effective stress then.
Yeah, okay. Effective stress, I have that information right here.
Just to see if there's some, like, how is it varying?
Yeah.
Okay, so
So
see
this is good.
now it's flat. Perfect. That fixed
Yeah.
that. How do we sorry, it's not increasing, but it's
No,
flattening.
it's not increasing. It
Yeah.
matches. I think it matches very closely to the material curve.
Okay, so how do we view the same type of information? Can you look at strain in XY?
We can. I think the
Shear
only way
strain?
we can do this is to actually, because these guys don't let me visual, like I can't, here, maybe this one. Oh no, this is the load. This won't work because this is, there's a die involved, so that's not going to work. Summary doesn't give us anything. So the other way that I usually go about doing this is to generate a report. And here we can specify
What you want to
the
export?
exact stress component.
Okay.
An XY export. And
And
then
then
we can also add
strain.
the strain here. Yeah, but yeah, look, yeah, the strain.
You can
Okay,
only
we don't have a.
export one at a time.
No,
Okay.
I don't think, no, that's
Oh,
not the
sorry, sorry.
case.
Don't do total strain. I think that's at the end step.
Oh,
Strain. Yeah,
strain
now. Oh,
effective.
guess not. Okay, just try that, whatever. Try that.
Uh,
Oh, look at this. Automatically makes a PowerPoint for you.
no, it won't create. It'll just create this. It's taking snapshots of this. Yeah, I don't know why I clicked PowerPoint. I should have just generated. I don't know.
So, are you going to get like data from that, or it's just images?
We can get data from that. So I actually exported a text file. So
Okay.
along with the PowerPoint slides. So
Okay.
these things are always under def report
Okay.
and state variable. You can pull up the strain. Yeah, but okay. So we get the strain components. We're gonna have to do some magic to
Okay, but I think
isolate
that's go towards the end of the simulation, like halfway through. Sorry, not towards the end.
halfway through
Around
step
the around the
50.
yield. Yeah, maybe. So this looks like it's
Uh,
20,
no,
23 megapascal, 23, and then 0, and then you have 23 in shear, 0, and 0. So why are you getting the shear and the axial?
uh, well, yeah, well, we're not, well, uh,
Yeah, I'm still not totally sold on the boundary conditions if we're doing or I think what we're intending to do is 100% correct, but we're not inputting them correctly into DEFORM. Like it's
mhm.
we're misinterpreting the way that it's constraining it.
Okay. So Andrew, what I can do is I could contact the form and set up like a web meeting if
Sure.
that is an option. And we can probably share a screen and guide and basically walk through what we're doing. Um,
Yeah, I wish I could have helped you more than this right now, but
well,
I
I mean,
think what we're trying to do is intent. We're doing the right thing. It's just not coming. It's not applying correctly in the form.
mhm.
Is there a way that you can graph this right now, like these
Yeah, I
numbers,
can.
import them?
Well, it might take some time because I'm not. See, we can get the direct column here, or this column here, but
Yeah.
that would involve writing the UMAT, and that's something I've never touched, so I can't do it.
Okay.
Um,
Let's go back to the
I'll have
result.
manually if that's the case, which
Yeah,
is
no,
not too
don't do that yet. Okay, where is this the result here? This one?
That's
This is
the
the post-processing?
preprocessor. Results
Okay.
is the other one.
Okay. Let's go back to how you were able to graph
Okay,
the
here,
equivalent stress.
this one is the results one. Equivalent stress. So to graph equivalent stress, I went to summary of outputs, summary, and then just go all, and you can look at the strain. Yeah, it's funny. I don't know why this stuff doesn't populate because it
Because
clearly shows that we have these
because the
values.
summary I think is only doing effective quantities. You might have to have like an advanced option. What are these other ones beside it?
So these are nothing. These are like region of interest kind of
Oh,
stuff.
okay.
Load
Load
stroke curve
stroke.
doesn't apply to us. We can do state variable between. We can track a point. Maybe that might.
Yeah, try that.
Yeah, we can track a point. Uh, we can do report too, actually. Let's get rid of these guys.
And does the point have to be a node or it can be the integration point?
I don't think we have access to integration points. I think it has to be. What's going on? Fixed point, moving point. So let's pick this point here. Yeah, the GUIs sometimes
Get glitchy, yeah.
not set. Okay.
Just highlight everything, see what happens.
It works sometimes and it doesn't, and I don't know if there's something that oh, there we go. Okay. So point one, let's go with that. And I think I can output the state variables for that point. So
Stress.
XY, right?
Yeah. Yeah, and the problem is the output quant, like that CSV file or that text file, you can't
Yeah.
graph it easily. So like I'm just trying to look for a way that in the form you could graph the quantities easily?
Uh,
When you have load versus stroke, can you manipulate what the coordinate axes are? Like try going back to load versus stroke.
for the load versus stroke, it's not going to do us any good because our die is very small and it's not even touching any of this stuff. Um, but we can set up like an artificial condition where we have a die that's
Okay, where's the die?
it's very small. It's somewhere here. Like it's somewhere out here somewhere. I don't even know where it is. Actually, here. Do this.
Okay, that might be part of the problem because there's contact in this problem now with the
No,
die.
no. So I never assigned contact in this problem.
Okay,
So contact here, there's
nothing.
nothing. This die is, I need to have a die or else the simulation doesn't run.
Okay,
So it's not, it doesn't even get
okay.
calculated.
Go back to. So what happens with I know just humor me if you click on
Yeah,
for, force versus stroke.
yeah. Let's try that. So you want the die? I think we'll get a flat number or the workpiece. I guess that's
Yeah,
better.
sure. Yeah, so torque, load. Yeah,
Yeah, it doesn't give you.
try any of these loads. I just want to see if it's something,
It's
if
flat.
there's anything.
Yeah,
Well,
it's always
Z is the direction that there's no load, so try X.
okay.
Still nothing. Okay.
Y is 0 as well. Yeah, these aren't going to give us. These are
Okay.
load stroke, right? So we won't get anything there.
And what
Let's
are
try
the
the
other
point tracking.
options? Sure.
Huh?
Okay, keep going. Don't worry. Point tracking. Yeah. I just don't like that you have to export the point data. Like there's no way to graph. Like when you had the yeah. Go back to the
We might
graph.
be able to just do it this way then. Let's just try this way. Uh,
Very glitchy.
yeah.
Yeah, I think you had to click object. No, what do these do?
These are point selection wizard.
Okay, go back. That's no good. Click that. Maybe control select or shift select. Uh, that's dumb.
It takes a little bit of time, but it does work.
I feel like it started working when I said just select everything, but I don't know.
Okay. Okay, see, it lets me pick this point. That's okay. We can change this. Have to go
-1,
this
I think.
0.5. Okay,
Yep.
that's good. Track.
So now when you try to create a chart or a plot, does it give you the point tracker as an option?
I think we can do it that way. Summary. No. I feel like I've done this before. I just can't remember how. Here, I think we can figure this out.
Are you guys using the most up-to-date version of DEFORM? or is it outdated by a few years?
There might be another version that's a bit higher. This might be the second most recent. I can't remember.
I don't think that, obviously this is not a feature that they just would have integrated. This has probably been around for
Yeah.
since the beginning.
Mhm. Yeah. So we can do this. I need to go. Oh, the configure the wrench button. Local material axis.
Huh,
Stress. Strain.
that's good.
CSV file.
It looks like in the help documentation there, they have it graphed right within the viewport window.
Yeah. I they do the.
Maybe not. Maybe that's from Excel.
I think when I do this and I click track, it might give the plot. Nope. Okay. How do they do it? Let's read. Track button points for track for all database when state variable plot will be displayed along state variable graph. State variable plot. Depending on saved. This can find state variable plot. State. Okay. Oh yeah. Well, we're picking up point one, P1.
Okay. So change
But
the
it
quantities for P1. The,
quantity.
like right now you
I
have
I
the
can't.
effective stress being graphed.
Yeah. There's like this won't let me.
Okay, how do
It
you
won't.
configure like what happens? Can you change the axes or whatever here? Uh,
Yeah. Sorry. Say that again.
like how do you configure this plot for this, say this curve here? How did you do that?
So I that's done through here, and then what I did was
So instead of it
I
showing effective, can you show something else?
if I do displacement and then I do track. No, that's not right.
Yeah,
Okay.
go back to the plotting feature, the summary. It was in summary. Uh,
Load step. No. No.
yeah, so how did you get, there was a drop-down menu that had like stress and the effectives were non-zero, but
Yeah. So that was here. So I went show graph. Here we go.
yeah,
That gives you string.
there's no way you can edit the,
So that drop down menu was through, like I click this configure button.
okay. No, before you even were doing point tracking, just to show the effective stress.
Oh yeah. Okay. So that
How
was
did,
through summary here,
summary, yeah, yeah.
and then I
So
go
what,
all, and I scroll down to. I don't know why. I don't know why this is not showing now.
because you're on the first step, probably. Go
Oh
somewhere in
yeah.
the middle.
Okay. You're right.
Okay, what does it have for stresses? Okay. So how can you select not the mean? Yeah, see, like these are not what we're thinking. This is x over r, y over z. These are different quantities.
Mhm.
We want, yeah, x, y over r, z is 0, but we just want x, y.
Yeah. 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 That's right.
But anyways, let's see what the effective stress for that point looks like. Like just graph the effective stress of the
For the
I
point?
don't know. Yeah,
Yeah,
like
so for the
that's what
point,
this
we'll
is
have
doing,
to,
right?
no, so this I think is getting it for the entire element. So for the point, what we need to do is, let's go track now here. Configure. I don't know what this element value is. I haven't. Value track. It's element data interpolation. So effective stress for P1.
Yeah, there, that makes sense now. So now, if you had multiple points, like because you only have one element, it's showing line over line, I think. Or it's showing you what the other plot had. Okay, go track now. What does that do? Nothing.
So it brings up this point tracking. We selected that point, right? So P1. I configured it conventional whatever. And then displacement and
Okay, get rid of
stress.
displacement on the point tracking. Yeah, only stress.
Stress and display. That's good.
Okay, now click that. Or tracking, I guess. Track now. So that's the stress at that point in time. Uh,
Can't change anything from here.
in the help document, do they have effective stress graphed or is it something else?
It's effective
Shit.
stress.
Yeah, it's possible that's all they allow you to do.
Yeah. Yeah, and if you're changing that, you can't change it, but you have to go through the UMAT stuff, and
Okay.
you, you
Okay,
have
so
to.
at the end of the day, we just need to fix why the boundary conditions aren't getting applied properly. This is all
Yeah.
stuff that we gotta look at after, but just to make our lives easier. But I think I'll think a little bit more, but as far as I can tell, you're applying the boundary conditions correctly, at least of what you're intending to do. And I think what you're intending to do is correct. We just need to
Yeah.
make sure that deform is, why is there axial stresses? There shouldn't be axial stresses.
Mhm.
And the other reason why I wanted to graph these quantities is because we could go through the plot and maybe the axial stresses start very low at
Yeah.
when you get to 17 megapascals and 21 megapascals of shear. But where we're looking at them, you're really, really far in the deformation. And because of
Mhm.
that, the axial stress, because the whole element's rotating a lot, it might be causing that. Like maybe if you go back, okay,
You have to
how did
right
you,
click it.
yeah, there was a way to bring up the results on this window here. How did you do that? Like the stress and the
Results.
strain, the tensor components of the stress and strain.
Okay, so that was through the element button here.
Yeah,
To close this up.
yeah, this one.
What is this? Okay, no, these are not important. And then deformation general gives you. You can't change this either, right? So it's
Okay, but
centered.
the stress you can look at the individual
Yeah, yeah,
tensor components
yeah.
here. Okay, so what happens if we look at the beginning? So you still have you have really you have equal stresses here, and they so it's doing what you expect. You see the numbers for x and y.
Mhm.
They initially start at 0, the very first increment, 33, then they
Yeah,
peak at 36, and then they start going down here.
yeah, yeah.
And then the shear is actually going down, which is what you'd expect. But why is x and y not 0? And this YZ shear should be non-zero. YZ shear in the YZ. Both of these should be, sorry, the same thing, but we're constrained. Yeah, this might be the problem is we're constraining these to be 0. Okay, do this. Go back to your uh, boundary conditions. Okay, so this whole face is fine
Yep.
and leaving it fixed. This node down here, remove the constraints on that.
Uh, constraints on the Y or
Both the Y and the Z.
okay, this thing got messed up. I don't know what we're looking at here.
Yeah, it might
Oh,
be.
this is the old one. Okay. Gotta close that.
I understand that you think it's gonna rotate, but let's see what happens.
Yeah, that's fine. Y, get rid of that. And then
And then the
X.
X2, yeah. Uh, yeah, do it.
That's Y.
Like
X is
this
fixed.
doesn't make sense, but I just want to see if the result changes from doing this.
Mm-hmm.
It should change.
Yeah.
Well, the way you had it is still correct.
Free boundary condition. Yeah, it does starts to twist. Looks like.
Oh shit. Okay, let's see the beginning. Okay, let's just see if the stresses now are 0 in those other two directions. So this is good. This means it's doing what you're telling it to.
Mm-hmm.
Yeah, see, you still have X and Y stresses. So what I don't get is why is it only twisting on this one corner? Where orient it the way that it was when you were setting up the boundary conditions.
That's the way it looked initially. It's getting pulled. Maybe we should look at it from the top. Oh no, that's not gonna work. This is better. Yeah.
So then these are the two nodes that are having displacement applied here.
Yeah. Yeah.
Okay, go ahead. Stepping through.
Oh, this is sorry. This is flipped. This is the constraint in 3 axes.
Yep. Okay, keep stepping through. Yeah. Okay. Why
Right.
is it doing
This
this?
makes sense to me.
Yeah, this is what it should be doing
Yeah.
with the boundary conditions that you have, but with the other ones that you have, it shouldn't be doing that. The ones that you had previous to this.
Boundary conditions. Velocity boundary conditions.
What happens if you remove the z? Yeah, that might be the problem. Is that there's a z constraint here when
Mhm.
you apply those boundary conditions. It's not allowing contraction in this direction.
It it can
It
contract
should.
in the Z direction, but
Ideally, it should, but like even now, this side length. I don't know why I keep rotating this. This side length here. Oh, geez. This one here
yeah,
is not changing.
it's not moving. Okay, I see. Yeah, so
Or sorry.
I'm just looking at the velocity boundary condition information
Okay.
here, or the help menu.
Apparently.
It's not gonna help. Okay. Independent XY for set to 0 for symmetric conditions. It's 2D, actually 3D's right here. Symmetric boundary conditions.
Yeah, I didn't even see that option to be honest, but this is a older version of the GUI, it looks like.
This is the 2D one. I think that's why. Like this right here.
Yeah.
This GUI is a 2D one. The 3D one is right here. I just clicked on the symmetric boundary condition.
Okay.
Symmetric plane. Symmetric plane. But that's.
Yeah, do that.
Do this.
Set a symmetry plane. On the face that you're constraining in the Z direction,
Yeah, let's try
set a
that.
symmetry plane. Go back to these are incorrect boundary conditions, what we just did. Go back to the ones you had previously. How's life otherwise? We've been talking about this for too
Life
long now.
is, it's a same
Don't ask
song
that
and
question. I know
dance, same
the
song and
drill.
dance every day.
Yeah. Until you get past your comprehensive exam, don't ask that question, and then for a year you're okay, and then after that, don't talk to anyone and ask that question for another whole year.
Yeah, there's a whole bunch of stuff happening. I can't really focus because part of my brain's occupied with this comp exam, and then friends are doing things, but can't really pay attention to that stuff. Where were we? This is. Yeah, I want to go to the gym too, but I don't know, with the uptick in cases, I'm not confident. Okay, so this is what we initially had, and symmetric plane.
So the nodes that you've defined, those four nodes over here, that's your
Yeah,
symmetry plane, because that will
yeah.
impose through thickness stresses 0.
Mm-hmm.
So point, how do you define? Oh, so you just need a point and then the normal direction. So pick this point. or any point on that face. And then the right-hand rule, I think, will define the normal direction.
The normal is 1, 0. And actually, that. I don't know what's going on.
It doesn't matter which point you click, I don't think.
Okay, point 1.
As long as it's there.
Normal is 1, right? This is 0. No, it's not right.
Yeah, it is, no? That looks right. Negative 0.5, 0, and 0, right? Here?
Yeah, yeah,
And
and
then the
normal in the
normal
Z
is,
direction.
yeah, that's fine, I
Okay.
think.
So this is our symmetry plane then.
Correct, so it should be these 4 points here.
Yeah.
So you set up the rest of those boundary conditions.
Wait, okay. Why am I still getting the same thing then?
That's changed. That's what it should be. Okay, click add. Because you've manually text edited it. Oh, so it's just showing you, I think, the direction here, maybe. Like, you're saying, why is it showing you 2 nodes lit up? Is that the
Yeah, I
problem?
guess, okay, whatever. It says normal about the symmetry plane, right? And this is the symmetry plane.
Yeah, I think that's okay, don't worry. Just
Okay,
set up the rest of the boundary conditions and run it. If it makes a difference, then we'll go back and look at these with more detail, but let's just make sure it changes the result.
okay. So this is going to be 0, yeah. 1.
Yeah, the same boundary conditions you had 2 runs ago.
X, Y, Y, Z axis.
All 4 of those points. You can't multi-select and then just click enter?
Yeah, I can multi-select. I have to click plane here.
Okay.
No, wrong one. This guy here.
Wrong
It's
one.
not here.
Wrong one.
Huh. That's weird. I don't know why it's not letting me do it now. But whatever.
Yeah, okay, just do it one at a time, it's fine.
So,
Yeah, it's not the most friendly, like, Abacus is shit too, but
yeah,
HyperWorks is
Abacus
really
is so
good.
much better than this. No,
Okay,
this
you're
one's
still
also.
missing one, I think. Okay.
Y is fixed.
Yeah. Yeah.
X is
Oh,
fixed.
no, you got too many. Oh, no, that's okay
Oh,
actually. That's from the symmetry boundary condition. I think it added that automatically, but I'm not sure.
yeah, this is not going to.
Yeah, I'm not sure if it added that automatically from the symmetry boundary condition, but remove it if it's just from what we were doing before. See
Yeah,
what
I can
happens.
remove it and
Yeah,
then re-add the bottom ones. Y is good.
yeah.
X is good. And then symmetry
Symmetry
plane.
still seems to be there. That's fine. Okay.
Rotation. Okay.
Now the velocities.
Yeah, so that's why.
Got it. Got it.
That's
Yep. Got it. Go.
velocity
No.
and symmetry plane cannot be defined together on the same node. That makes sense. So I think what we need to do is symmetry plane here, and then define
the velocity there.
Velocity here.
Okay, try that. Just remove the one node from your velocity definitions.
The one node from the velocity. So
yeah, you have two nodes here. Just remove the one that's on the.
Yeah, but yeah, okay. So this is good according to this guy. I don't know if these fixed Z will cause any issues. I don't know if this fixed Z will cause an issue, but let's see.
So the other thing you can do is the symmetry plane. Define it as this here, this phase.
Yeah, yeah, okay.
Instead of the
I
other
think
one.
that makes more sense than what we have here, because this is, when I click this, it selects this node, and I think that symmetry plane is defining something along the x-axis, it seems, even though it seems kind of counterintuitive.
Okay, so select like this node now. Okay. I think this is automatically taking the normal vector from this point, which I don't know how it has a normal vector because it automatically populated this.
Yeah.
So just change them. Yeah. Okay, that should be good.
This would have to be minus whatever 0.5. Okay, so this is good now.
Nothing got added here though.
Yeah. Right
okay. You have to click add. Okay, go ahead. 001 and 001.
Yeah, so that this defines this face here. So then
okay, yeah,
I'll
nice.
Constrain
exactly
this node, right? I can do all here. All. Oh no, that's wrong. Oh, no, it's okay. One. No, that's wrong. Oh, I should have done that. That's good. Let's add. Okay, velocity. Whew, okay. 0.1y. It's good. This is good. Good. This should work. I have a feeling this thing's gonna work.
Yeah, so this is really a 2D problem that you're making into a 3D problem, and the way to get rid of the through thickness constraining effect is by making a symmetry plane. Hopefully.
Hopefully, yeah, that'll be the case.
Because that'll make it impossible to have stresses in that direction.
Yeah. Well, that's interesting.
Okay, which nodes are getting pulled? Which are the ones that we deformed?
That's fine. I think what's happening is, so this is symmetric. This face here is symmetric. Okay, so I might have to, I guess.
Yeah, just
constrain these two.
So
points,
constrain this one and apply the velocities to this one.
Yeah. Okay.
And hopefully it runs. Like you were worried that you didn't do that because you thought it wasn't going to run, but
yeah, let's try that. Yeah. I mean, it's just a matter of like rotating the Rubik's cube, right? Just how many
that's why this is so confusing with a single element. It's great once you get it running and all you're doing is changing indices, but in the
Yeah,
beginning it's a pain in the butt.
yeah. Okay, so this is fixed. This is fixed. This fixed. This fixed. Oh no, I messed up. Oh, it's okay. Good. Y, X, Z, 1, 1. Okay,
Yep.
should be good.
Okay. Yep. Converge, converge, converge. How long does like forging simulation take in terms of runtime?
Uh, so if I have that adaptive remeshing turned on for, yeah, if I have it turned on for 30K element simulation, it takes about 30 minutes out, or maybe less than that, like, yeah, 20, 30 minutes for 30K element simulation. I'm running on 4 CPUs. I have a license to run on 4 CPUs.
Do you have your desktop from your office at your house here, or you're using Eng?
Remote, yeah, I'm using remote desktop.
Yeah, okay. And which one are you? Do you have like, oh shit, somewhat better?
Yeah. Yeah, it's, I don't know
Okay, go to
why.
the stresses now. The stresses should be smaller in the X and Y, I think.
Nope,
Nope.
still the same thing.
Jeez. Yeah, maybe it's best that we talk to the DEFORM guys,
Yeah.
because I think we're trying to do the right thing, and now we're reaching to find other boundary conditions that will give us the result that we're looking for. But so this is the problem, is that the two nodes that you're applying the velocity boundary condition for, it's not
Yeah.
allowing it to move in the Z direction. The rest of the
Mm-hmm.
plane here has symmetry, but this node is actually not expanding in the Z direction.
Mm-hmm.
So it's imposing,
Causing, yeah, stress on it.
because in the process of moving it in the X and Y direction, it's not allowing it to move in the Z.
Yeah.
So what
Yeah.
about adding a force? Change the boundary conditions to forces now. Use
Instead
like
of the
one
velocity,
one
right?
newton instead of the velocity,
Yeah, yeah, yeah.
because it's just that one node now that's kinked out. Everything else the same, just those two velocity boundary conditions.
It's these guys, right?
Yeah, same node, same everything. Just now use a force.
Um,
1 newton, I think, worked reasonable.
Oh no, it's not gonna work. I have 4 nodes selected.
The other problem that you face is I think you know way more about this than your supervisors do, and asking for help is exceedingly difficult when you're having results meetings and and they're like, oh yeah, just look in the manual, and it's like, no.
Yeah, I think I've gone through a lot of that manual. It's been a year. I've been on this for a year, so like fully committed to this for a year. So.
When did you actually start your PhD? A year ago or longer
PhD,
than?
yeah, it was a year ago, last
So like
summer.
your comprehensive is technically pretty early then, because normally it's like 16 months to 2 years, I think,
Yeah,
into.
I know. It's funny because on the website, in the engineering website, it says after 4 terms you need to do your comp exam. That's what it says.
Really?
If you're going from, I think it's because I went from a master's directly to a PhD. I think that's the reason. I think that's the
Oh, yeah, yeah. Okay. All right.
yeah.
Let's see.
Yeah,
It's
it's
dumb. It's dumb how you're not constraining those nodes in those directions, but applying the velocity inherently
mhm,
is constraining them, I
constrained.
think.
Yeah, I don't know. Yeah, still expected. Still
Same
same
thing.
thing.
The deformation, go to the form. I guess the deform shape is nothing because it's 1 Newton.
Yeah.
Okay. Yeah, we need to talk to deform then.
Okay. Okay, I'll set up an email. I'll send them an email and I'll loop you into it and try and secure a date and time
Okay.
for a
If this
conference.
doesn't happen before our meeting on Wednesday,
Yeah.
either we delay that meeting or we try and make this meeting with the forum happen tomorrow or later today, which I doubt, seriously doubt, because it'll probably take a few days. But
Yeah, because I
um,
know they have to get the tech. Because when I talk to them, I get the sales guy, and then the
yeah,
sales
yeah.
guy connects with the technical guy, and then we set the meeting up.
Okay. All right. I'll back you up if you want to delay that meeting on Wednesday because of obviously just progress, but lack of responses from um, the forum.
Okay. Okay. And what's your? I guess that is our next immediate step, right? Like to verify this element model and then move on to the actual shear hat testing simulation. Yes, that's the plan
Yeah.
of attack.
So I think that Bezos didn't mention that in the email, but I think presenting the forging simulation correlation between shear hat physical test results, because
Yeah,
that's also a novel thing that I don't think anyone has published.
yeah,
So we have the shear hat physical test results, and then using this material model with these Hills coefficients, these are our calibration constants, and this is
hmm
how we had to fine tune them slightly
yeah,
to get it to correlate to the experimental data. That's exactly what I think we should do for shear
hmm
hat, and then we say, okay, this is like a research grade sample, and then here's how we're simulating um, the forging operation of the control arm.
hmm yeah. Okay.
That might be a separate paper because I think Bezod wants us to be more academic in nature, but we'll see. The shear hat is a compromise of being the single element academic and then like the real component practical. So I think it's the best compromise.
Okay. Okay.
Because the other thing that you're not getting with the shear hat testing is the strain distribution in the sample and the strain rate distribution and all of that, and the effects of friction and that type of stuff. So that'll help you dial in all those other system level stuff. Because right now, in a single element, you don't have any of that. This is only
Yeah.
material model, where the
Yeah.
shear hat has all those things built in. But it seems like the the lack of correlation between the input equivalent stress curve, like the flow stress curve, and the output curve, that's
Yeah.
matching well now. Um, just these axial stresses that are induced in us trying to recreate this pure shear case is weird. It doesn't make sense.
Okay.
Let's see. Okay. Yeah, that's all I can think of right now, unfortunately.
Oh, this helps, Andrew. Thank you for taking the time to do this, because it's a good sanity check.
Yeah, for sure. I agree. I mean, I learned a lot too, but in the process of a lot of these things you don't need to look at in that detail when you're doing the whole component.
Yeah. Yeah.
But
For this.
okay, cool.
All right. I'll send